Hey everybody, today we're going to talk about exponential growth and decay. For exponential growth, if you guys watched the introduction video, you will know that that is a function that is getting larger and larger. Think of the scenario with the golfing bet. And exponential decay is when the function is decreasing. So for example, depreciation, or if you're paying off a loan, the loan amount will get smaller and smaller and smaller as you pay it down. So we have two equations that we'll be using. The growth one the only difference is it will have a plus, and the decay one will have a minus. So we'll be adding a rate and subtracting a rate. Together, this will be our growth or decay factor. So that is the factor by which the function is growing or decaying at. Okay, so let's look at our first example. This is similar to the one I did in the introduction video, so you can practice it one time. So we have the initial amount. We have a truck purchase for $28,000, so that is going to be our A. It is called our principal or beginning value. When we talk about money, it's called the principal, or it's just the initial amount if it's not talking about money. Since it says depreciate, I know that I'm going to do 1 minus the rate. The rate is 20%, so as a decimal, I'm going to plug it in as 0.20. And then X is going to be our years. I'm going to put T so that I remember that it's time. You can use X or T, whichever one makes you happy. All right, so now we have an equation. How much will the truck be worth in 2 years? So what you're going to type into your calculator is 28,000, and 1 minus 0.2 is 0.8, so I can go ahead and simplify that to make it easier to type in the calculator. And then 2 is going to be the exponent. So go ahead and type that into your calculator. I only have an old school calculator at home, but you may have something else. Oh, we don't need to type this into y equals because we don't have values. You can just type this onto the regular screen. So 28,000 times 0.8 to the second power. So $17,920 is how much the truck will be worth in 2 years at the 20% depreciation rate. All right, so after how many years of owning the truck would you reasonably be able to sell it for $6,500? So this is giving us an ending amount. So this is our Y value. So really what I want is, so this is still my initial amount, and I still have the same rate. I'm wanting to know how many years. That's the part I don't know. How many years is it going to be worth? How many years will it take to be worth $6,500? Now, I haven't showed you how to solve this kind of equation yet because we need to learn logs, and I will be showing you how to do that in the next unit. So since we have not yet learned that, what I'm going to have you do is put this part of the equation in the y equals, and then we can look to find when it's approximately 6,500 at this point in what we know. So in the y equals, I'm going to put $28,000, 0.8 to the x power. All right, so go to your table. I'm looking in the y column for when the truck is approximately $6,500. And I can see that at year 7, it's $5,800. And year 6, it's $7,300. So it's somewhere between 6 and 7 years. So somewhere between 6 and 7 years, the truck will be worth $6,500. So that's how we can estimate it. We'll learn how to calculate that more precisely later. All right, let's read scenario number 2 and look at a different kind of decay function. On federal income tax returns, self-employed people can depreciate, that's a key word, the value of business equipment. Suppose a computer valued at $3,000 depreciates at a rate of 30% per year. Write an exponential function to model the value of the computer, V of t, so that's going to be my function, after t years. What is the value of the computer after 2 years? So my initial amount is $3,000. It's depreciating, so I know I'm going to do 1 minus because when it's depreciating, I'm always subtracting. That means it's going down. 30% with 3 t years. Okay, now I'm going to plug in 2 for t to figure out how much the value of the computer will be. So 3,000, that would be 0.7 if I subtracted 1 minus 0.3 is 0.7, so I went ahead and put in 0.7. Oh, that's a little better. To the, what was it, 2 years? Yeah, 2 years. So that is $1,470 is how much the computer would be worth after 2 years. So you can kind of get a feel for what depreciation is. Okay, scenario 3. This year a total of 64 teams qualified for the college basketball tournament played during March and April. Each round, half of the teams were eliminated. That's an important part. Write an equation to represent the teams, T of R, so they're telling me what the name of that function is, that remain in the tournament after R rounds. Okay? So, if half the teams are eliminated, is this an exponential growth or decay kind of scenario? If you said decay, you are correct because the number of teams is decreasing. It's going down. Okay? So we're starting with 64. Remember, this is always our initial amount. What are we starting with? So we're starting with 64 teams. And half of the teams are eliminated. So half would be 0.5. And R is the number of rounds. I also could have written this as 64 times 0.5 to the R power. That would be the same function. And it didn't ask me any questions this time, so they just wanted me to give an equation for that one. Okay. This one did not print on my printer, so I kind of tried to write in at least the important information on this one. But this is a really important question because a lot of students get confused on the wording of this one. So I want you to think carefully about this. It says a particular type of bacteria divides into 2 new bacteria every 20 minutes. A scientist growing the bacteria in a laboratory begins with 40 bacteria. How much bacteria would there be after 2 hours? So, we're going to call this function B of t for bacteria, and over time is our 2 variables that we have. We know we start with 40 bacteria, so that's our initial amount. Now, this is the tricky part. If the bacteria is dividing into 2 new bacteria, is this exponential growth or decay? Students hear the word divide and they think it's going down. But if I have a single bacteria that is dividing into 2, I'm actually having double the amount of bacteria every time because these 2 will then split into 2 more. And now I have 4, okay? So each time the bacteria divides, I'm having double the amount of bacteria. So be careful that you don't hear that word divide and you automatically think that that means it's going down. Because technically, if each bacteria divides, we now have double the amount of bacteria. So this is going to be a growth function, and it's actually growing by 100%. Same as the golfing scenario at the introduction video. So it's growing at 100% because each time it is doubling. So t is still going to be our exponent. Another way we could write this is 1 plus 1 is 2 because it is doubling each time. We're going to have twice as many bacteria each time period that passes. Keep in mind that the time period, the t here, is representing every 20 minutes because that's the increments that they told us that it doubled in. So we're going to keep that in mind when we answer questions. Okay, so the question is how much bacteria would there be after 2 hours? So in 2 hours, how many 20-minute sections are there? Well, I know that 2 for 60 minutes makes up an hour. So 2 hours would be 6 20-minute sections. That's 2 hours worth, right? Okay, so what I need to plug in here is 6 because there's 6 20-minute sections in 2 hours. All right, so what I'm going to type into my calculator here is 40 times 2 to the 6th power. So that tells me that there are 2,560 bacteria after 2 hours if it continues to double at that rate. Very good. All right. In 1990, the tuition at a private college was $15,000. Over the next 9 years, tuition increased by about 7.2% each year. Write an equation giving the cost C at the college T years after 1990. That's a key part, after 1990. Okay, so initial amount is 15,000. Is this an exponential growth or decay kind of scenario? You're right, it is a growth. And how did you know that? This word right here should have clued you in. Increased, right? If tuition is increased, it's going up. So we know this is going to be a 1 plus kind of scenario. And I'm going to take that 7.2% and change it into a decimal. Be sure and kick your decimal place 2 times. So that's going to be 0.072 when I make it a decimal in T number of years. So there's our function. Now we can use that to calculate whatever year. See, the power of being able to write a function is we now don't have to calculate out each year. We can use our function to jump to whatever year we want to. That's the power of mathematics, is identifying a pattern so that you don't have to do all the math. All right, so we're going to estimate, use your calculator to estimate the year tuition is $20,000. So that is a cost. So what we're really saying is, when is y going to be 20,000? This is 1.072 if I put that together, if I add those together. Okay, so since, again, this is an equation I've not showed you yet how to solve, we're going to use our calculator, put this in the y equals, to be able to find approximately 20,000. So in the y equals, you're going to put 15,000. By the way, if you don't have a graphing calculator at home, I put on the cover page of my Canvas a free resource to download a TI emulator calculator. They put it out during this time to help you out. So go to the cover, my home page of my Canvas page, and I put directions on how to download that emulator for yourself. To the x power. All right, so I'm going to my table, and I'm looking in the y column for approximately 20,000. Well, I can see it's approximately between 4 and 5 years. It's just a little after 4 years. I can see that it's almost $20,000. So a little after 4 years. All right. Second part is asks us to estimate the tuition in 2017. So we want to know what year this is, basically, because remember, this is years. A common mistake is students plug in 2017 in for T here. Don't do that. Don't do that. This is the key part. After 1990, I want to know how many years later this is. Okay, so 1990, that would be 27 years later. So the secret is to plug 27 in for T. You cannot put years in for T because the calculator doesn't understand years. You always need to translate it into, say, years since. So make sure you always translate it into something the calculator can understand. Okay, so I'm going to plug in the calculator 15,000 times 1.072 and to the 27th power. That's what you're going to be typing in. Notice there's no x's, so we're plugging it onto the home screen. Times 1.072 to the 27th power. So 98,028. And I'm going to round to 2 decimal places because this is talking money. Money, we should always round to 2 decimal places. So $98,000. Wow, that is a big jump in tuition. If that rate continues, we can see how much more expensive this college is. Unfortunately, tuition rates are growing. I don't know if it's growing that quickly, but it's definitely been growing. Okay. All right, I wanted to show you one scenario of how to calculate an equation if you just have data points. This is especially valuable in what's going on with the coronavirus right now. So this is how statisticians are doing these analysis type data. I collected the worldwide cases of coronaviruses on a weekly basis. So here's the dates, and here's the number of cases that was reported weekly across the world. This is the worldwide number. So I want to find what is the trend, what is the pattern that's going on right now. So what you're going to do is you're going to plug into stat. Remember, we've been using stat edit to calculate equations. And in L1, remember, we can never put dates into our calculator. We need to translate it for the calculator. So what you're going to do is I'm going to start this and label this week 1, because this is really like week 1 of our calculations of our data here. So this is week 1. This is going to be week 2, 3, 4, 5, 6, 7, 8, 9. So now I have given them values that we can put into the calculator. So my first column is just going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. L2, I'm going to put my cases. That's my Y values here. So 580, 7813. Be very careful, because remember, if you put in bad numbers, we are going to get bad answers. Garbage in, garbage out. The calculator only does exactly what we tell it to do. 314. So I'm really trying not to make a mistake here. Okay. I typed them all in. Now we're going to run a regression to get the equation. I'm going to make the assumption that it's exponentially growing. We'll run a linear regression too, just to see how close it fits. Remember, we know how to see which data line fits better. So stat calc, scroll all the way down to option 0. You should see XREG. That stands for exponential regression. So we're making the assumption that it's going to exponentially grow. Okay, and so I have an equation. Notice I'm missing my R and R squared. That's the correlation coefficient. It tells us how close the data is to that line, or it was the coefficient of determination is the one that was helpful. So if you do not see that, you can go to catalog, second catalog, and remember, we want to turn diagnostics on. That way you can see how good the data is. Let's see, diagnostics on. Okay, now I'm going to run my regression one more time. Now I have the R squared value. So that tells me how well it fits. Remember, the closer to 1, the better. Right now it's at 0.757, so it's not awesome. I'm going to look at it a little bit closer, but I'm going to record the equation. It told me to do an exponential regression, so I'm going to go ahead and record that, and then we're going to look at it a little bit more detailed. So I'm going to round to 3 decimal places. The tricky thing about this is they can get exponentially more off the more we round, so we try not to round, but I can't help. This is big numbers. I'm going to have to round at some point. So the more accurate you want the equation, the less you should round. So keep that in mind. 1.787 to the x power. All right. So this currently, according to this equation, is our growth factor. So according to this data, this 9 weeks of data, this is the rate at which it is growing. Okay. So if this continues to grow at this rate, that will predict how many cases we have unless something happens. We know that we're analyzing this because we're constantly waiting for that growth factor to go down. That's what we're waiting for, the turn to happen. Okay, so I'm going to look at, just out of curiosity, so my R squared, I'm going to write this down, was 0.758 for argument's sake. And just out of curiosity, I'm going to run a linear regression just to see if it's any better. And it is a tiny bit better. That's actually good. That means we're not growing we're closer to growing at a linear rate instead of an exponential rate. Okay, so I'm going to still stick with my exponential because we're studying exponential functions. Y'all are really good at linear growth. I want to show you why it's giving a 0.75 correlation. Let's look at the graph for just a second. If you want to see the graph, you need to hit second y equals, it says stat plot, and turn that on, because then that will help us see, it'll help us see the data points. We'll get to see the points I'm going to show you in just a second. Okay, so I'm going to put in our equation here that we just calculated. 594, 1.787 to the x power. Okay, I just put in the exponential equation we just calculated, and I'm going to hit graph. I can't really see anything. A helpful thing is if you are looking at statistical data points, the zoom feature that's awesome is called zoom stat, because it zooms into those data points that we just put in. Okay, so those dots each represent the data points that I put in. The line is this equation that we just calculated. Now, look at the dots. They are not super close to the line, and that is why we're not getting a super close r squared, not very close to 1. The closer those data points are to the line, the closer this will be to 1. You can see by looking at the data points, it almost looked like it started to flatten out here, but then it started to grow again. So that's probably why this equation is not fitting perfectly, but this is the best exponential equation that fits the data points we have. Now remember, the more data we put in, the better the equation. So maybe if we track this for more weeks, or if we took a daily reading, we may be able to get a more accurate equation. So statisticians will look at this and be like, okay, so what's happening? Why did it start to flatten here? What made it take off again? These are all questions that they need to analyze when they're making decisions about what should we be doing? What is our next step? Is it getting better? Is it getting worse? Like, these are all the things that we can look at and how math can help us make those decisions. Anyways, I thought that was really interesting, and we're going to be doing a project next week looking at your own set of data, so I wanted to show you kind of how to think through that. Okay, the last thing I want to talk about with you today is how to do compound interest. You probably had done this in Algebra 1 maybe, or in 8th grade. It's been a while, but it is a really helpful formula to use because all of the formulas we've done so far are based on simple interest, meaning it is not compounding. What compounding means is as you collect interest, let's say you put your money in a bank, you put $1,000 in the bank, okay? And every time you collect interest and add that money to your account, you are now collecting interest on a larger amount. So that's what compounding means. If you compound monthly, that means each month the bank calculates up your money and it dumps that interest into your bank account, and now you're collecting interest on a larger amount. So that's what compounding means. In the real world today, we have computers and they actually compound continuously, which I hope to talk to you about because that's a really interesting number that you'll see. Some of y'all may have seen the E. That is what comes into play when we compound continuously. Continuously means it is continuously compounding. Okay, so we're going to start with compounding by different increments. So the only change in the formula you'll notice is our rate is divided by the number of times that we are compounding, okay? And out here, N is also the number of times compounded times T. So it's the same formula with those two small changes. So you deposited $15,000 in an account. First we're going to calculate it annually. So I'm going to calculate it how we were doing it before, and then we'll calculate it monthly. So if we do $15,000 in an account and it's earning 2.5%, so that's 0.25 when I convert it to a decimal, in T amount of time. Find the balance after 20 years. All right, so we'll just type in 15,000, 1.025, 20 years. So that will equal, if we plug in 20, that'll be 2, 4, 5, 7, 0.92. So $2,457.92. So let's compare that to if it compounded monthly. So if that compounds monthly, the only difference is, oh, I cannot do that. I'm going to use my new formula now. So 1 plus my rate is still 0.025 divided by n. Since this is monthly, n, remember, is asking how many times it is compounded in 1 year. Well, if it's monthly, that means it's going to compound 12 times. So that is 12. And up here, it's going to be 12 times the 20 years. N is how many times it's compounded, that's 12. And T is the number of years. So that's what we're going to type into our calculator this time to see how it compares. Oh no, I missed a 0 on that answer. It just means it's going to be clicked over one more time. I'll retype that one in real quick. Y'all probably are already correcting me on that one. So, yeah, it should be just bumped over one space. So that should be 24,000.9. Oh, I'm just going to rewrite it. 24,579.25. Okay, sorry about that. Okay, now let's go back to calculating the other one. 15,000, 1 plus 0.025 divided by, make sure you put it in parentheses if you have an old school calculator like me. You want to make sure it does order of operations correctly. And 12 times 20. All right, I got 24,717.96. So when you compare those two numbers, you can see it's slightly more when it's compounding monthly. And that is because each month, it's collecting the interest, and now we're calculating the interest on a larger amount. So that's why it's going to come out to be a larger amount. All right, last scenario. We have a car that is purchased, a new car is purchased, and a $3,000 loan is taken. Okay, I was misreading it. $30,000 loan is taken. The interest rate is 2.9% compounded monthly. How much is owed after 3 years? So we are going to do 30,000 is our initial amount. This is how much is owed. So we're really not paying on this loan yet. It looks like it's just collecting interest. So if we take out a loan, assuming we're not making any payments, it's going to collect 2.9% interest is going to be added to how much money we owe. And this is, again, compounded monthly. So I'm going to use 12 for my n because that's how many times it would happen in 1 year. So that's what you're going to type into your calculator. So let's say it had asked for daily, compounded daily. What number would you put in? 365 days in a year, right? Okay. What if it said semi-annually? That would be 2 times. So think about how many times that would happen in 1 year is what the question is asking. All right, last one. Type it into your calculator, and you should get 32,723.47. I typed it in earlier. Hopefully that is correct. All right, so that is our introduction to exponential growth and decay. So continue to practice these examples until you got the hang of the formula, and I hope you enjoyed this.